Okay, so hello everybody. I'm very pleased and happy to present to you Dominique Manchon from Université Clermont-Auvergne, who this evening will talk about post groups, post Lie algebras, and Lie group actions. Please have your time.
Thank you very much for your invitation. So I must say that I'm not at all a specialist of knot theory, but I was driven to these post-group actions by post-Lie algebras. I'll tell you the story. And it turns out that post-Lie algebras and post-groups are also linked to solution of the Braid equation. So this is the link with knot theory. And let us start right now. Okay, so it will be based on joint works with several people. Mahdi Al-Kaabi from Mustansiriya University in Baghdad in Iraq. Kurush Ibrahimi Fard from NTNU in Trondheim in Norway. Hans Muntekos from Bergen. And also Yuan Yuanchang from Henan University. Okay, so I was driven to this subject by differential geometry. So let me recall a few points. If you look at the smooth manifold, you look at the vector fields on your manifold. Of course, it's a Lie algebra because you have a Lie-Jacobi bracket of vector fields. And an affine connection is a covariant derivative operator. So you have these very famous relations here. If you multiply the first vector field by a C-infinity map, you can sort the C-infinity map out. So you have this linearity with respect to the first argument. But if you perform nabla x of fy, you have rather a kind of Leibniz rule. So you have two terms, f nabla xy plus derivating f in the direction of x and multiplying by y. And as I am quite an algebraist, I like to flip the triangle by pi over 2. So x triangle y will be nabla xy. Okay. Okay, so the Lie-Jacobi bracket is given by just this. The ordinary Lie bracket given by the composition product of two vector fields. But of course, if you compose two vector fields together, you get a differential operator of order 2. But if you perform the bracket like this, you find back a vector field. Okay, so your space of vector fields is now endowed with two products. The triangle given by the connection and the Lie-Jacobi vector Lie bracket. So it's called the framed Lie algebra by Alexei Gavrilov from Novosibirsk, and I'll take about him a bit later. Okay, it's a module over the C-infinity maps, but in general, you don't have any compatibility between the triangle and the bracket. Okay, so now, of course, classically, you introduce torsion and curvature. Torsion depends on two elements. It's given by this formula. Curvature depends on three vector fields and is given by this formula here. So, and I have a very nice property. Torsion and curvature are C-infinity of M linear with respect to all the arguments. So 2 arguments for the torsion, 3 arguments for the curvature. So they are not independent. You have 2 Bianchi identities between both. And of course, you can build some more complicated expressions by manipulating torsion, curvature, and derivatives of those. So just for completeness, I recall very quickly the two Bianchi identities. So these integrals just mean sum over circular permutations. So each integral like this is a sum of three terms. And the sum over circular permutation of curvature here is given by a difference of two terms, the derivative of the torsion and the iterated torsion like this. And okay, what is the derivative of the torsion is given by this formula here. If you think about it, it's just applying a Leibniz rule on this term, which is X triangle on an expression of three terms, the torsion, the vector field Y, and the vector field Z. Okay, so it's quite natural to define the derivative of the torsion in the direction of X like this. Second Bianchi identity involves four arguments like this, and it involves the derivative of the curvature and an iteration of the curvature on the torsion like this. And the derivative of the curvature is given by a similar expression. It's the similar trick to define this, to define it. Okay, so this is very classical. It dates back at least to Kobayashi and Nomitsu in the 60s. Okay, so now let me give some two basic examples. The first easy example is the flat torsion-free case. For example, your manifold is R to the n, so you have a canonical connection. You just write down your vector fields in coordinates and derivating, so performing X triangle Y, it is just derivating each coordinate of your Y in the direction of X. So there's no mystery here, and it's easy to see that torsion and curvature vanish. And then your triangle is not random. You get so-called left Preely identity. So that means that the associator of your three arguments may not vanish, but it's symmetric with respect to the two first variables. So Preely algebras appeared independently in the 60s in a work by Winberg and a work by Gerstenhaber. But we can also cite an important paper by Arthur Cayley in 1857, where, of course, the word Preely doesn't appear, but it's already there in some sense. Okay, the next example is the flat constant torsion case. And as an example, if you let a Lie group act on a smooth manifold, you can easily build up a connection which is flat and with constant torsion. So flatness condition. So okay, this is a variant with two arguments, but okay. Big R of XYZ, it's small r of XY applied to Z. Okay, and flatness condition is that the curvature vanishes, and the constant torsion condition says that this expression, the derivative of the torsion, vanishes identically for any XYZ vector fields. So in that case, you look at your space of vector fields endowed with the triangle and the bracket, and it's going to be a Postli algebra. So Postli algebras were introduced by Bruno Valette in 2007, and a very closed notion called the algebra was introduced by Muntekus and Wright 1 year later. For a totally different purpose. The purpose of Bruno Valette was purely algebraic and combinatorial. He was interested in homology of partition posets, and Winterkos and Wright were interested by numerical schemes on homogeneous spaces. And it is interesting that two very different motivations led to the same mathematical object. So what is a post-Lie algebra? It is a Lie algebra endowed with a bilinear product denoted by a triangle, so that you have two compatibility conditions here. The first is very natural. It says that if you look at a triangle, the bracket B and C, you have a Leibniz rule. You distribute your triangle over both arguments, B and C, here. The second axiom is a bit more mysterious. So you look at what happens when you perform a triangle B, sorry, a bracket B, triangle C. And the right-hand side, it is just what I would call the pre-liator of A, B, and C. So more precisely, you look at the associator of ABC and you subtract the associator of B, A, and C. And so, in other words, a post-Lie algebra with vanishing bracket becomes a pre-Lie algebra because if your bracket vanishes, the first axiom is empty. And the second axiom says that the right-hand side vanishes. And that's exactly the pre-Lie algebra relation. Okay. So post-Lie algebras are interesting in the sense that if you have a Lie bracket, you have a second one. This double bracket here, defined by this expression. It also defines a Lie bracket. It's a 5-6 lines computation. You have opposite post-Lie algebra. So you change the sign of the bracket, and the black triangle is defined like this. And this bracket, this double bracket, is called the Grossman-Larson bracket. And both Lie algebras, both post-Lie algebras, the original one and the opposite, do share the same Grossman-Larson bracket. Okay, so from post-Lie algebras, three authors here recently defined the notion of post-Hopf algebras. So, in a nutshell, the universal enveloping algebra of a post-Lie algebra is a D algebra in the sense of Munteko's right, and more precisely, it's a post-Hopf algebra. So what it is, it's a co-commutative Hopf algebra. So by Milnor-Moore theorem, it's the enveloping algebra of some Lie algebra, but together with a linear map denoted also by a triangle, such that you have a kind of associative version of the post-Lie axioms. First of all, you have a Leibniz rule like this, but think about, yeah, okay. So you have more than two terms on the right-hand side. So you look at the so-called, you look at the co-commutative coproduct of your Hopf algebra, and this is Swidler's notation. That you have the behavior of the triangle like this. And U triangle, V triangle W, like this. It is U star V triangle W. And this is the explicit expression for U star V. So again, in terms of the co-commutative coproduct, using the product on the triangle. So it turns out that this star product here is also associative. It shares the same unit than the original product. And here there's a technical invertibility condition. So the left translations by the triangle here. Okay. This map, L triangle, admits an inverse for the convolution product called denoted by a beta triangle. Okay, so in a post-Hopf algebra, you have two Hopf algebras, two co-commutative Hopf algebra structures, the original one and the one with the Grossman-Larson product, with the same coproduct, the same unit, the same co-unit, but the antipode is different. And you have a formula linking the star antipode with the original antipode. Okay. So now, if you choose two elements x and y in a post-Lie algebra, G, you look at the universal enveloping algebra of your post-Lie algebra, it is post-Hopf, and you have this relation here. So star is called the Grossman-Larson product. You can recover the original product with this formula here. And what else? Okay, so if this Hopf algebra structure is the enveloping algebra of a post-Lie algebra, this Hopf algebra structure is isomorphic to the enveloping algebra of the post-Lie algebra, but endowed with the Grossman-Larson bracket. Okay. So let me now discuss construction due to Loïc Foissy a few years ago. So you can generate a free post-Lie algebra from a magmatic algebra. So you start with a vector field endowed with a bilinear triangle, and you look at the free Lie algebra built up above V, okay? And there's a unique way to extend the bilinear map triangle to this free Lie algebra by, roughly speaking, forcing both post-Lie axioms. So it's very natural. So, for example, if V is a free magmatic algebra generated by some color set C, small g is a free post-Lie algebra generated by your color set. And it's known that it is given by formal iterated brackets of planar rooted trees decorated by your color set. So the triangle map is given on the planar rooted trees like this. So it's called the left grafting. So you graft the first tree and the second on the left everywhere you can, and you sum up. I insist on the fact that this grafting is not pre-Lie because it's important that, for example, here in the middle term, the long branch is on the left, not on the right. So it's an avatar of the magmatic algebra. And then there's a unique way to extend this to the free Lie algebra. And if you look at the enveloping algebra of this post algebra, so you get the tensor algebra over V. So it is the 3D algebra generated by V. And the basis is given by the planar rooted forests decorated by the color set C. Okay. Okay, so now I have to briefly describe the K-map by Alexei Gavrilov. This object is maybe not very well known, but it's interesting. So you start from a vector space endowed with a bilinear triangle, and you look at the tensor algebra. So it's the enveloping algebra of post-Lie algebra, so it's a post-Hopf algebra. You have two Hopf algebra structures. And Gavrilov defines a map recursively like this. So it's an induction on the length of the words. So k of 1 is equal to 1. K of a letter is the letter itself. And k of a word of length n is given by this formula here. So it involves k of words of length n minus 1. So you have this first term here. x1 tensor k of the tail of length n minus 1. and minus the sum of k of, and here inside the big parenthesis, you have a word of length n minus 1 once again, because the x1 is used to contract with xj, to look at the letter x1 triangle xj, and the total length is n minus 1. So, for example, on a word with 2 letters, you get this difference here, and on 3 letters, you get a combination of 6 terms. The word itself, 3 terms of length 2 and 2 terms of length 1 with double triangle. Okay. One can remark that k of a word is the word itself plus corrective terms of smaller length. So it's obviously a linear isomorphism, because you can write down the matrix of k, which will be triangular with ones on the diagonal. The inverse is even more interesting, because you can express it in a non-recursive way. So k inverse of x1 up to xn, sorry, is a sum of terms indexed by partitions of the set 1 up to n. And this term here, depending on the choice of a partition, is a word of length, the number of blocks of your partition. So the blocks are ordered by their max. And for any block, you sort out the letters in the block in increasing order. You iterate the triangle and you put the parenthesis on the right, like this. Okay? And so the formula is completely explicit. So, for example, k inverse of x tensor y is this sum of 2 terms, because you have 2 partitions, the coarse partition and the singleton partitions. And for a word with 3 letters, you have 5 terms corresponding to the 5 partitions of a set with 3 elements, etc. Okay, there's a theorem by Gavrilov saying that this map, K, is a Hopf algebra isomorphism from say, the Grossman-Anderson Hopf algebra onto the Hopf algebra here. So let me make an important remark here. If you take post-Hopf algebra, there's absolutely no reason that you have a Hopf algebra isomorphism between these 2 structures. But it's true in the free case here, right? And not only it is true, but you have an explicit isomorphism. So in particular, if you restrict your K to the post-Lie algebras themselves, you have a Lie algebra isomorphism between the Grossman-Larson Lie algebra and the original Lie algebra. So, because, okay, basically, these 2 Lie algebras are 2 avatars of the free Lie algebra generated by V, and K is the isomorphism. Okay, so now let me go back to differential geometry, and I will describe the post-Lie algebra of Mundekos on right. So you start with a smooth manifold. You have a smooth right action of a Lie group G on it. Small g will be the Lie algebra of big G, and G to the M, it will be a notation for the Sinfini maps from M with values in this Lie algebra. So G to the M is a post-Lie algebra. So the original Lie bracket is just given by the pointwise Lie bracket, okay, like this. And the triangle is given like that. So let me explain. For any map, a Sinfini map from M into G, you have a vector field sharp X on the manifold. And then you let this vector field act on the map Y, like this, and to evaluate at point X. This gives you the triangle. And it turns out that you have a post-Lie algebra, and the corresponding Grossman-Larson bracket reflects the Jacobi brackets of vector fields. So you have this formula here. So beware that we have three Lie brackets here. We have the Jacobi Lie brackets of vector fields. You have the Lie bracket of the post-Lie algebra, and you have the Lie Grossman-Larson Lie bracket. Okay. So if the action is transitive, any smooth vector fields on your manifold is equal to some sharp x, maybe in a non-unique way. Otherwise, you reach only the vector fields which are tangent to the orbits. Okay, so now I come to post groups. So post groups have been defined very recently by Bai, Guo, Sheng, and Tang. So a post group is a group endowed with, again, something denoted by a triangle, such that, first of all, the left translations like this are group automorphisms. And secondly, if you double triangle like this, you have this right-hand side with A star B given by this expression here, A dot A triangle B. It turns out that G star is it's also a group. It's called the Grossman-Larson group, or by some authors, the subjacent group. And both groups share the same unit. And G star acts on G dot by automorphisms. So each element has an inverse for dot and inverse for star, and they don't coincide in general. You have a notion of opposite post group. You reverse the order of the terms for the product, and the black triangle is given by conjugating the white triangle like this. And both share the same Grossman-Larson group. And by Guo, Sheng, and Tang proved that the Lie algebra of a post-Lie group is a post-Lie algebra. And the recipe is very much like what you do for Lie groups and Lie algebras. You differentiate twice the triangle of the group to get the triangle of the Lie algebra, like this. Okay. And the notion of opposites match. This is not a surprise. And by Guo, Sheng, and Tang proved that this notion of postgroup, in fact, it's not so new because it's equivalent to two older notions. First of all, the skew braces by Guarnieri and Vendramin from 2017, and also to Lu Yan and Su's braided groups. So here the link with knot theory will pop up here. Okay, so let me give you a few words on this. So what is a skew brace? It's a set endowed with two group laws, dot and star, subject to this skewed distributivity axioms here. Okay. And this relation, with this relation, you can show that the unit for the first product, it's also the unit for the second one. And if you introduce the triangle defined like this, you make G dot triangle a post group. And conversely, if you start from a post group, you focus on the both products and start is a Grossman-Larson, and you get a skew brace. So it's quite obvious that both notions are equivalent. So for braided groups, is a bit less obvious. So what is a braided group? is a triple G with a multiplication and some map from G cross G onto G cross G, which will be proven to be a braiding. And so you want both relations there. So this relation is a bit tedious to describe, but if you draw, it's more easy. First of all, you can multiply two elements and two other elements and then braid, or braid first, but you have to double braid. This is this sigma tilde, and then you multiply, and you want equality. And the second axiom is a braided commutativity axiom, and it's drawn like this. And if you have such an object, it turns out that it verifies the braid equation here. And okay, so I know that by now Braid and Young-Baxter are synonymous, but in a Luyant and Shu paper, they made the distinction. Okay, let's keep this. And now I introduce the following notation. Sigma of xy, so sigma goes from g square to g square. So sigma of xy, it's given by x acting on y, and x on which y acts. Okay, and both maps, right harpoon and left harpoon, are respectively a left and a right action of G on itself. So it's a theorem by Lu, Yan, and Shu. Okay, and our four authors proved that for any post group, the Grossman-Larson group is braided. And the braiding sigma is given by this expression here in terms of the triangle. And conversely, any braided group with sigma written like this gives rise to a post group whose Grossman-Larson product is the star here. And explicitly, the triangle is given by the left harpoon, so the first leg of the braiding, and the dot product is given by this. Okay. So we proved with Madi and Kurush that the braiding corresponding to the opposite post group is the opposite braiding. So maybe it was a folklore result, but we reprove it. Okay. So as a consequence, what we call the pre-groups are the same as the symmetric braid groups, and there are also braces by Rump. Okay, so a brace is a skew brace which is not skew. That means that the first group law is commutative. So a pre-group is a post-group so that the group law is commutative. And a symmetric braided group is a braided group where the braiding is involutive. Okay, so now let me go back to Munteko's right post-Lie algebra. So we try to search for a post-group version of it. So you look at a set on which a group acts on the right. G to M will be the set of maps from M into G. So G to M is a group under the pointwise product. Okay. And you can define another binary product, the triangle like this. So F triangle G at a point X, it is J evaluated at X moved by F of X, like this. So the maps F triangle something are group morphisms, but we are not lucky here. G to the M is not really a group. So there exists a subset of invertible maps so that you get a group playing the role of the Grossman-Larson group, but curly G is not the whole G to the M. So there's a notion which matches what we want here. It's a notion of weak post group by Shun-Kung Wang. And this weak post group above comes from a post groupoid structure. So it's a recent paper by Sheng and Tang and Chu. Okay. But nevertheless, our post group is weak, is not a post group. You can differentiate twice. And if you do that, you recover the post-Lie algebra of Muntekus and Wright. So we proved this in our paper with Kurush and Madi. And let me conclude the end of my talk by a purely algebraic and combinatorial result in the spirit. So we wanted to build up a kind of free post group. And for this, we start with a magma, but not any magma. We start with a left regular diagonal magma. So what is a left regular diagonal magma? It's a magma M endowed with a triangle, a binary product, such that, first of all, the left translations are bijective for any A. And second, the big lambda, given by big lambda of A is equal to the inverse translation by A applied to A. We want that this big lambda map is also bijective. So these two properties look strange, but you have a lot of examples. For example, any quandle is a left regular magma. And it's a left regular magma with big lambda is equal to the identity. So maybe I should recall what is a quandle. So a quandle is a magma with a self-distributivity property. That means that if you have three elements A, B, and C, A triangle, B triangle C is equal to A triangle B triangle, A triangle C. So it's a self-distributivity axiom. And a second axiom for a quandle is just A triangle A is equal to A. Okay. So as an example, you can take any group and A triangle B will be conjugation of B by A. So a quandle, in a nutshell, it is what survives from a group if you just look at conjugation. Okay. So the example 2 is the free regular magma M generated by set X. So it is present in a paper by Juan Orza, a recent paper by Juan Orza in the language of skew braces. So in fact, he considers what could be the skew brace, the free skew brace generated by color set C. So as an intermediate step, he constructs what appears to be the free regular magma, regular diagonal magma generated by the color set X. And then it's possible to build up a free post group on it. And what we did is the following. For any left regular diagonal magma, we build up a free post group on it. So it works like this. You look at the free group generated by your magma. Okay? So here it is the canonical embedding. And here you take your favorite post group, G dot triangle. You give yourself any magma map from M into your post group. And then you are able to uniquely extend your phi into a post group morphism phi tilde here. So this is a universal property fulfilled by Fm. And with this, we prove that there's a unique explicit group isomorphism, big J, from the free group into the free group endowed with the Grossman-Larson product. Because it turns out that Fm is a post group, so you have a Grossman-Larson product, and both group structures are isomorphic. And its inverse K is a post-group analog of Gavrilov's K-map in a purely combinatorial and algebraic setting. Okay, so you have here some references, and it's a good point to stop, and thank you very much for your attention.
Thank you very much for the very interesting and inspiring talk. And now I will stop the recording and then start a Q&A session.